Handling Handling high explosives is one of the most unforgiving tasks in the defense industry. There is no margin for error and no second chances. For decades, factories relied on human hands, but even the most skilled operators are still human, slow, repetitive, and prone to error. Humans can only work so fast and with limited accuracy. Even minor errors create bottlenecks, delay production, and limit efficiency. But what if every step could be faster and flawless? Today, there's a better way to protect both people and mission continuity without compromising on control, accuracy, or accountability. Introducing the robot arm. It's a modern way to handle repetitive work in the manufacturing process with unmatched speed, accuracy, and consistency. Our system outpaces human labor, automating movement, minimizing errors, and streamlining workflow for maximum efficiency. The result? Faster production, fewer mistakes, and optimized output that means your team stays in control from a safe distance. Remote operation, full telemetry, instant shutdown, zero exposure with maximum reliability. Whether your mission is stockpile stewardship, warhead life extension, or final dismantlement, automation doesn't replace the expert. It extends their reach and preserves their safety. National security demands innovation that's not only smart, but safe. You've always protected the nation. Let us help protect the people who protect it. Handling
No more. That leads to better numbers and So this is an overview of our solution. This is what the robotic arm will look like very roughly. We'll be going more over that later in our prototype. So it'll have 3 prongs and the tips will be rubber in order to increase the grip of the highly explosive.
All right. And this isn't all just theoretical. This is stuff that's been proven to work in real industry, especially with transitioning from manual to automated manufacturing. You guys are obviously focused on efficiency, so I want to highlight the speed and labor cost aspects of the table. In industries across America, we've tripled the speed when using robotics, and labor's been cut in half, which is just a good bang for your buck, thinking about it like that. As you can see, just with the error rates, damage rates, and order accuracy, there's positive trends and improvements throughout all aspects of the process. But what's happening in other places across the country isn't really that important to you guys. What you guys are worried about is how we can bring that to Pantex and what it's going to look like at your company. So this is the good part when you get to do the Legos. I'm just going to click through that. I don't have to do it. But you guys, okay. So everything's going to take place inside of one room that's been certified, and it's going to have a human's going to power the forklifts, which is the door for the room is going to be a glass door. Forklift can enter, drop off a package. The example model here shows 6 barrels full of explosives, but obviously it could be more, and you could expand this to have multiple sets. This is the Aura. We included a barrier for entry, so that way you can't have any accidents with the forklift driving forward. Forklift exits. We have cameras around the rooms that is monitored from a remote location at all times, making sure that everything's okay with the process. Once they've confirmed that the load is set, there's going to be dual authentication using the keys, so the person driving the forklift and the person actually watching can both confirm that everything's okay and that it's sealed off. So at this point, the barrels have been sealed. Nobody's been interacted with them. The Aura arm will actually unseal the barrel, and we want to give you guys a close-up. So we kind of redesigned the barrels a little bit to make them easier for the robots to pick up. So it'll have some kind of knob, like a screw on the side that should be unscrewed, and then a lift, so it lifts off. This would be the packaging around the edges, and then the lid can be placed aside. Around the packaging, there will be small holes to put in the indicators and the silica gel to restock for the packages. The explosive material can be placed inside the machine that's being operated on. When it's finished, the barrel will be replaced, resealed, like so, and then it'll be confirmed by whoever's operating it. And then once each barrel is complete and they're all done for the entire crate, they can exit that. The forklifts will re-enter, take the barrel out, and exit, and then you can restock and refill over and over again. And obviously, this can be expanded across multiple industries, like with multiple types of machines.
So obviously, this is just one section of the whole production line, but ideally, we could implement this in sections. So if you feel like the CNC process is the most important, you would obviously invest in implementing Aura for the CNC first. But then we would have opportunities to expand functionally about all of the different processes. So that could be the X-raying, coordinate measuring, or the density test. Also possible future considerations. Right now we're doing the very bare necessity for automating the most important task of machining. But in the future, we would like to focus especially on expanding other automation steps. That includes processing the raw material, handling radioactive material, or even dismantling the munitions instead of doing that by hand. And of course, all the system would be certified by Class 1 Div 2 by a trusted government authority.
So let's talk about efficiency. With Aura, we're able to cut down time on tasks that would generally take hours to just minutes. For example, inspections that would generally take 2 hours can be done in 20 minutes now. Additionally, other tasks such as switching programs or unpackaging and repackaging can get done 2 times as fast. Overall, we'll see a 44% increase in efficiency for each step. Let's talk about feasibility. So, of course, there will be a cost to this. We're looking about $3 million to repurpose the building. However, looking at Pantex's current program, you guys are spending $1 million each year to do this. But however, with Aura, you'll be able to get profits in under a year, and we'll see a 225% increase in the production rate. So in conclusion, we want to improve. Aura would improve many factors, starting off with efficiency. It would make processes faster and just automate redundant parts of the process. Additionally, safety is very important to us. We want to keep all our workers safe, and we do this by reducing the amount of time that they interact with the hazardous material. Lastly, adaptability. Aura can be used and can be applicable to many different processes.
Okay, thank you, Team Aura. What questions do you have for Team Aura?
I have a question. On your, I see a man that you have operating the machinery. What other individuals do you have in that? Do you have just the one person going into the room operating that, or do you have a two-man, or what kind of verification process that you have?
So what our process is currently is whenever the barrel is loaded in, you have multiple different cameras clustered across the room with multiple different angles at the procedure and at the machinery. So when the door opens and the box is secured, it can be easily verified through a multitude of sensors and through direct human sight, the cameras, to make sure everything's in place good. We're closing down, letting this man come off his forklift, turn his key to let him know that he packed everything correctly. And then the man who's watching the camera, who's overseeing this operation, can turn his key. So overall, there's going to be no one in this area that needs to be extra besides someone who's monitoring it, the person operating the forklift.
So you have the other folks at a command station or operating center overlooking that process. Great, thank you.
Of course.
You mentioned in there that it would reduce the inspection time, and I see a prototype that is moving AG from place to base. But how is this going to increase or reduce the amount of time it takes for inspection?
Well, usually in the process when they have to move the AG out of the container and then they have to do inspection, we would be able to use the camera system to ensure that there's any paperwork that needs to get filled out about it can be integrated into the barrel itself, since we're redesigning the barrel. So that way all of the inspection stuff can be handled by the remote operator and sensors in a separate room.
And not to mention your coordinate measuring machine, and then your density test, and also your CT machine. We kind of notice have a very similar pattern in terms of unpacking that barrel, taking your high explosive out, putting it in the machine, letting it run, taking it back out, and putting it back in the barrel before resealing. And as we noticed, that can kind of be similar across multiple different processes. And so it's a little repetitive. So something robotics does really well is repetition. And so you're able to use this across many different of your systems at your own pace. So if you have something that's extremely important that you want someone to be overseeing and doing themselves, then you can have someone doing that. However, if you have other things that you're fine with letting a machine take over in terms of unloading and reloading, you can let this machine do it. It's all at your own pace. You don't need to implement it everywhere.
So you're not actually changing an inspection process, you're changing and reducing the time in the setups before and between processes.
Correct.
One real quick question. You mentioned the design criteria that the arm had to have the strength of one person. What does that mean exactly?
So when interviewing the Pantex people, they mentioned that each person would have to lift about 25 pounds. So the conditions for our arm is that it should be able to lift 25 to 30 pounds, which is the condition for a human.
So that arm has a capacity of 25 to 30 pounds. That's what you're saying?
Correct.
It would be higher than that, but it's expected to be consistent across 25 to 30.
And not to mention all the
How much do you think that pallet of barrels weighs?
The arm would not be moving the pallet at all. The pallet stays stationary in like a loading spot, and the arm would just need to remove the lid and then extract the explosive into the machining process. It could be CNC, X-ray, anything.
My question would have been centered, I think Dale already asked it around the inspection, going from 2 hours to 20 minutes. It would be a good area of improvement if that was the math behind it. I guess I'll pivot though. You mentioned fail safes. How do you envision those to work, and what's the purpose of having those?
We're actually very glad you asked that. We actually have some information prepared here. So we have outlined, not to be, of course, in case you already know, but some of the CD1, D2 certification and some of the processes that it needs to have in order to be that C1, D2 certified. And so we have some of our features, which include our fail safes, which include a 2-factor authentication for startup. That's the 2 turning and locks to make sure they both are saying that everything is good to go and everything's been loaded at both steps, the monitoring and the loading process. There is multiple fail safes, one outside the room, one inside in case someone gets locked in through any reason at all. And then also railing to make sure that forklift cannot drive too far forward and accidentally hit any sensitive machinery. And then we also have the specifics here. Because of it's the same material and nothing's really changing, you don't have to make an entirely new design for these rooms. You can keep the same designs for your storage rooms that you keep all of these barrels already in, just at different scales to fit everything. But everything is going to remain the same. You don't have to find any new processes.
Okay, we need to finish up. Thanks. Thank you, Terrell. Snap Shield, come on up.
So I don't want to block this part. Because when we hit sauce, it'll be off shots.
David, you got on the store? Whenever you're ready. Pick it again.
What happened to using rotary telephones? Or things like cassette tapes? How about floppy disks? Why did we ever stop using them? Well, that's simple. Because technology evolved. Because now, there's a better way. So why should we treat our high explosive facilities any different? Howdy, we're SnapShield. We're creating a product to increase the efficiency of high explosive plants, ranging from existing facilities to future facilities. Our solution will allow for greater productivity in old plants and more adaptability in new ones. Now, old facilities are still viable options. However, they're expensive, and more significantly, they're very inflexible. As the world changes around us, the needs for high explosive production and testing changes with it. In other words, we need more dynamic production infrastructure. And that's where we come in. Our solution, it's easily installable, and better yet, it's adaptable. It can be installed into older facilities to expand production. And in new facility construction, it'll drastically decrease construction times while still offering the same protection as traditional materials. So the world changes fast, but with SnapShield, you just might keep up. SnapShield, safety in a snap.
Howdy. Here at SnapShield, we are offering a innovative solution for adaptable high explosive facilities. In this rapidly developing world, innovation leads to charge, and making sure that modern industry is able to keep up with modern standards. High explosive testing facilities are stuck in the past. They're using half-century-old facilities with half-a-century-old standards. Why should we use half-century old standards when there are better solutions today? Modern technologies
So we met with our experts over at Pantex, and we determined there to be 5 design requirements that our solution must meet in order to be successful. Now, these can be split up into 2 categories: safety, which is of the utmost importance to Pantex, and efficiency. Now, that's where we come in. So let's dive into safety first. Safety means that our blast mitigation system needs to be able to withstand the byproducts of an explosion. That means that our mitigation system needs to be able to hold strong in pressures of up to 640 kilopascals. It needs to be able to block the penetration of fragments going at speeds of 3.5 kilometers per second. And the materials with which it is made of need to be resilient in heat of up to 3,300 degrees Celsius. Now, as for efficiency, that's really what SnapShield is here for. Pantex needs a transportable, flexible, and adaptable mitigation system, blast mitigation system. We can't keep going with these old facilities, especially when constructing new ones. So the 2 design requirements that we created that meet this are the width of our product needs to be under 2 feet. This is because the existing walls surrounding bays in Pantex's current facilities are around 18 inches. And that's at the very least. We want to maintain this number, if not reduce it. And lastly, the weight of our product needs to be under 3,000 pounds, because this is the forefront of our product: transportability, adaptability, and flexibility.
To take on our problem statement, we had 4 different whiteboards of solutions, but for y'all's sake, we're only going to talk about our 3 main ideas. Firstly, we had a partitioner wall idea that was composed of different layers of material and a non-Newtonian fluid to be able to split current facilities. Secondly, we had a honeycomb brick design composed of different composite materials and a honeycomb structure in the middle to mitigate any pressures. And finally, we had an absorbent manifold designed to dissipate force using its own weight.
All right. So the design team here at SnapShield has decided to go with the second of those solutions, which is the honeycomb brick. So the SnapShield brick is not like your regular cement brick in the sense that this one is actually a composite multiple layered sandwich inside of is a honeycomb structure. So this honeycomb panel, which is depicted here, is going to be made entirely of carbon fiber, and that is going to be instrumental when it comes to handling the compressive strengths of an explosion of a bomb. We could be talking PBX 9501 or HMX, other bombs similar in that structure. So the first layer is going to be a 1-inch barrier of steel. That steel is going to be the first line of defense when it comes to the blunt force of a material. Then the second layer is going to be a 2-inch thick piece of reinforced Kevlar. And that reinforced Kevlar is going to be what stops the blast fragments and the fragment mitigation process for that one to reduce all the energy, if not all of it, from going through and hitting the rest of the processes. The next stage is going to be a 1-inch barrier of carbon fiber. That one's going to give the tensile strength to the brick so that it's able to withstand the force of any shockwave or anything of that sort. And then finally, we have our bread and butter, which is our honeycomb design. So the honeycomb design is going to be set up in an axial format so the carbon fiber strands can actually really withstand the compressive forces. And we studied, and based on our research, by formatting it this way, we're able to allow the compressive forces to be multiplied throughout, so that way we can have a compressive strength of about 200,000 psi. So by setting up this way, when we have the brunt force coming out this direction, we're able to maintain majority of those forces and stop the crumbling and mitigate all the fragments from coming through on this one. And most importantly is the modularity aspect of the brick. So obviously we weren't able to put it on the model over here, but the brick is going to be able to be interlocked with the brick at the same time so that it can be constructed into a wall of however many heights, whatever dimensions that would be needed for this project.
Okay, now, what does all this mean? What do we bring to the table that isn't existing in current technologies? First up, scalability. Currently, we need more productivity. That is the crux of what we're trying to solve. We're trying to increase the productivity of your facilities, and that's where we come in. So we can use our snap shield bricks to basically retrofit your old facilities. You have a lot of facilities, but we interviewed your colleagues at Pantex, and they said we always need more productivity. We just don't have enough space to do it safe. So whenever you're doing like low scale explosives testing at your labs, and you have empty space, you can use our solution to basically split it into and be able to have 2 different production lines going safely. And that's why it's compatible with old and new facilities. But also when you're making new facilities, if the production plan changes while your if the manufacturing, if the things you need to do are changing, and you need to change, our structures will allow you to, instead of having to deal with reinforced concrete, you just take our cubes, pick them back apart, and restructure them to what you need them to be. And they are compact and quicker to assemble. So what this means is whenever you're constructing a new facility, instead of spending months weaving rebar and filling it with reinforced concrete, you can instead reduce that time to weeks, just because it's basically Legos. You get to snap them together. They're secure links, and safety in a snap. That's our whole deal. So that about wraps up our presentation. So we will now be taking questions.
So I got a quick question on it seems like a pretty ingenious solution. My concern would be as you start putting your Legos together, your bricks together, are there inherent structural weaknesses at the seams that a blast would cause a problem?
Definitely, and we thought about that question when we were constructing the makeup of this box. So what I mentioned earlier is that it interlocks, right? And then yes, there are definitely possibilities that at the seam points, at the connections, it can become weak points, right? So as this is in the testing stages, there are definitely possibilities that we were looking at where we could put maybe a Spalding sheet on top to essentially give a smooth finish to the entire wall so that those weak points wouldn't serve as forms of like breakage or any kind of like weak points that could like break apart in there. So we would be putting like a flat sheet that would essentially cover it. That's one of the possibilities that we were thinking of. Also thinking about redirecting the blast in other directions using angled walls was another concept that we're thinking about. That would be best to answer your question.
And to kind of add on to that, we also thought about potentially like expanding it to where we could have rods reinforced through like the overlay bricks, so it has increased inner like connected functionality, kind of like we would do with other reinforced structures, but on this scale. So different potential solutions.
Got a question about dimensions. I didn't see any dimensions of the bricks. Are they single size, one size fit all brick? What about changing directions, making a corner, anything like that? If we're trying to give us some flexibility, we're not just talking about a single straight wall.
Yeah, that is definitely something that we did think about. So essentially when we were creating this model, when we were creating the concept, we're essentially using this as like a standard size. But as the customer may need other like uses or corner pieces as you're talking about, it definitely can be suited to those. We just want to prove the concept and prove the technology is going to be able to be viable for a solution when it comes to blast mitigation and fragment mitigation. We want to make sure that that was the crux of what we were solving. But this concept can easily be adapted into a corner piece or maybe larger pieces, smaller pieces. The dimensions right now for the size that we'll be talking would be about 4 feet by 3 feet with a 1 foot depth. We try to keep the depth a little bit less so that it's not too much space that's reduced from the existing bay area. So the dimensions can change as needed, but right now we're just proving the concept essentially that the materials will work.
We've also been looking at the different chambers that we use because we have chambers and we also have cells. So we've also been looking at the different shapes these bricks could take. We've looked at pentagonal shapes, square shapes, and we can also manufacture them in any shape that the facility requires.
I captured at least 2 of the 3 options that you presented at the beginning, non-Newtonian, the honeycomb, and I missed the 3rd one, or I didn't write it down. Can you talk about what's the biggest benefit of going with honeycomb, and what's the biggest thing that you may be giving up without going with one of those other 2?
For the honeycomb brick, it was more have one thing to fix all problems, because we've also researched of implementing the honeycomb bricks into the other designs, into the absorption manifold as well, because it helps a lot with mitigating issues, especially with the honeycomb device. There's a lot of research on it to project that shape.
So, and the most important aspect about the honeycomb design is that the carbon fiber setup, which is the whole purpose of the honeycomb, is developed in the axial orientation. So when you have carbon fiber, the axial orientation allows for compressive strengths to be at least multiplied throughout. It's able to hold a lot more compressive strength when it's oriented in a certain way. So when you manufacture, it's oriented in that fashion so that it'd be able to maintain that compressive strength. That's why the honeycomb design was one thing that's very attractive to us, because of its application in aluminum senses and aircraft or senses like that.
Your axial direction gives you the compressive strength, but it doesn't give you the flexibility. What about, is there a trade-off in that? Why would you say compressive versus the flexibility with your steel and your...
Definitely. There could be a higher material cost that comes with it, but the main trade-off that we're looking at would be the material cost. However, we took this into consideration when we were making this, and we knew that when you have a compressive strength like that, after a long time, the longevity will prove to pay for itself, essentially. And that's why we went with more of an axial direction rather than a transverse direction, which would be more of a kind of crushing force rather than one that would stand a direct force from an explosion.
I also would like to add on. Okay, wait, we're going to have to stop there. Thank you. Come on, get down there. Let's
If you can read, I can't read that. Look around.
We could prefer to have it just two. Yeah, we need to. You ready? Whenever you're ready.
tool. As you may know, there are over 120,000 special tools at Pantex. What do we mean by special tools? We mean stuff like workbenches, we mean test stands, we mean hoists. We're not talking about just your normal screwdrivers, your bolts, your nuts, your hammers. Hundreds and thousands of tooling parts enter daily at Pantex. That means manual labor. That means repetitive tasks. What does that result into? Fatigueness and repetitiveness. Now, ladies and gentlemen and judges, raise your hand if you are energetic at 9 a.m. at work and at 5 p.m. you're exhausted, you're drained. Raise your hand. Great, me too. We get it. It's the natural human tendency to get exhausted and drained. Over 43% of workers are sleep deprived. That's bad. What does this lead to? This leads to productivity losses. You can lose over $3,000 per employee annually. You're not just losing money. You're losing your close friends and family just because of a failure inspection, just because you got tired and exhausted. So what's the main problem here? Human error.
So, the problem here, let me provide you guys some context. At Pantex, there's hundreds of product and quality technicians. Now, let me ask you guys the questions, judges. Do you really think all of these technicians provide consistent quality tool inspection? No, they don't. Why? Because these tool inspections are very repetitive. And repetitive leads to fatigue, and fatigue leads to decrease in productivity. Now, the main problem we're trying to solve here is how do we ensure quality automation while minimizing human error, right? Now, why are we focusing on human error? Human error costs company revenue. Why? Because they take time. You have to pay them. And also, most importantly, they have unstable tool inspection reports. So during an interview with one of the Pantex mentors, we found out that an employee who works 6 to 8 hours has a 25% decrease in productivity. Now to Auto Tool Incorporation, we know that your businesses need security. They also need profitability. Now, we will deliver that.
All right, so we have a problem, and in that problem, we need to make sure that we are scoping precisely to what problem we are solving. We don't want to cast too wide of a net here, so we decided to focus on geometric inspections. We are aware that these parts and these tools that you guys are inspecting are subject to electrical and also material inspections, but we decided to focus on geometric inspections. Let's be the shape and size of the material. Also, we're going to assume that there are legible part labels. We have confirmed this with members of your team at Pantex that most parts are labeled legibly. And finally, we understand that Pantex manufactures and designs many different tools that help with the operations there. And so we're going to leverage these CAD files that are already used to compare with the expected design.
So, design requirements. Now, one of the first requirements that we need is geometric detection. As you said in one of the scoping, you can't do the biggest tools that they have at the facility, and this geometric detection is going to be able to measure and find the different instances and parts and different defects within it over time. Tool size accommodation, as I said, there's up to 6 feet wide different tools they have at Pantex. We're going to be focusing on a 2 by 2 by 2 cubic foot accommodation size, so the volume's going to be 8 feet cubed. That roughly is 80% of the tools at Pantex, as we've talked to some of your employees. And we're going to reduce the time of inspection by 50% through this machine or whatever our product is going to be. So data collection. Our data is going to be not only put on the SAP, which we know Pantex is currently using on the business side of things, but it's also going to be using some AI tools integrated within it in order for an easier application of the data. Tool tracking. Now, what I like to say is a health bar for these tools. It's going to be showing how the tool is used over time and how it's degrading. It can even go from a preventative way to take out these tools to a predictive way. Lastly, it needs to be automated. So obviously we can't do 100% automation. A human is going to be in the room or they're going to be doing something. We're going to do 90% automation, 10% human interaction.
So these gave us our possible solutions. As you can imagine, a coordinate measuring machine came to mind right away. It seems good. It's got good detection, but as you can tell from our graphic, we didn't feel like it really
hit home with what we were trying to accomplish. So we also thought about 3D photographic scanning, and we thought about autonomous humanoid robots. We thought maybe one of these would give us what we're looking for. But as you can tell by the graphic, nothing really solved the problem we were looking for. So in a bold move, we're going to try to combine all 3 of these into one solution.
So, as Josh so nicely put it, we're going to take these parts that are individually labeled, we're going to combine it with multiple different technologies. So, my friend Hadi here, he's going to actually act as our robotic arm. So, he's going to take a tool or a part, he's going to take it from a bin, and he's going to place it in our system. Now, we're going to use artificial intelligence to actually read which tool is within what was placed in our system. And now we're going to use the CMM, the coordinate measurement machine that you guys are familiar with, to track different shapes and sizes and features of this piece and compare it with the CAD. And now from there, we can place it in either a pass or a fail bucket. And we can continue to do this. And one other thing is that we can leverage the data. So we're taking data from these differences between CAD and the real life, and we can measure it over time. So let's say hypothetically, we see on this part HDI 01. We notice that there is a 0.01 inch deviance from expected. Next week, 0.03. Week after, 0.05. We're seeing that trend go up. Now imagine that, scale it up, and we can track individual tools' health over their lifetime. My name is Noah Johannesson.
I am Joshua Peterson.
My name is Arti Devat Kumar.
My name is Sidya. And I'm Hadi Chaudhry. And together, we are Untitled. Thank you.
Now we look forward to any questions.
How long did it take you to make that video?
5 hours.
Can you tell me what so you combined 3 things. I saw the robotic arm and I saw the coordinate scanner. What was the other, wasn't there a...
So the digital scanner is what we're using to track the serial numbers of parts we track the data together.
Okay.
Talk a little more about AI and how you incorporated that into your decision and into the overall success of going to.
Yeah, absolutely. So we're using AI in 2 different ways here. First off is recognizing the actual part. So reading this part number, this is AI. And then also doing the data analysis. And so AI was crucial to our success here because us as humans, we don't have the time to go and look at these data points over and over and over again. We actually heard from personal anecdotal evidence that it's kind of word of mouth here. You're not going to remember that you looked at this tool 2 weeks ago and it had a 0.01 deviation, and then later it's 0.05. This stuff is hard to track. So we're addressing that using AI.
Thank you.
Does that answer your question?
It does.
You guys made some assumptions based upon the size of ports. I think you said this will address about 80% of what we have. Is there any thought to scaling this larger?
It would be readily scaled larger, just how much money you want to spend, and it's part complexity dependent. So it can't do so much systems like an entire tool. It's doing pieces of the tool.
Is there an option to take this past geometric testing? Have you thought through other testing mechanisms?
There most definitely is, but given our scope and time, we decided to just focus on the geometric parts.
What would be some of those other ones that you could expand to if you?
I couldn't tell you off the top of my head.
That is so good. All right. Good job, gang. Okay, Barrett Tutta, come on up. You've got my clicker. Who's up with clicker?
Right there.
Okay.
So this is a team. Black. Basis. David. This is you got this. And click. Could you never start? Yes, sir. That's what we learned. Okay. Whenever you're ready.
Russia carried out new strikes on the country, including this massive
Saudi
wave
Arabia
of
and
drones.
Pakistan have signed a mutual defense pact just days after Israel's strike
between
on
an axis of powers see the U.S. and other Western allies as an enemy.
Threats to the United States are growing bolder and more powerful every day. In order to protect our country and our families, America needs to increase efficiency in weapon production to match these threats. Current Pantex CNC machining for high explosives requires intense safety precautions due to heavy human interaction with the materials. There's a dire need for change in the current system to ensure national security. Barracuda addresses this need for efficiency by cutting out over 50% of human interaction with high explosive machining. We've implemented automation to the CNC process through combination mill and lathes to reduce transportation between machines and a programmed robotic arm to move high explosives throughout the process. Our solution would decrease steps in the CNC process, increase the speed of production, and streamline the process further. Efficiency affects all Americans, and it starts with Barracuda at Pantex.
Howdy, judges. Howdy, everyone. Howdy. We are Barracuda, and at Barracuda, safety and efficiency are always not going to be mutually exclusive. And Pantex, we want to help you.
So we got the opportunity to talk to a few Pantex employees this weekend. More specifically, we got to talk to them about your current CNC manufacturing process. And as you can see, it's a long process. It's got plenty of steps. And there's processes inside that, like packaging material for transport and waiting for those slow bay doors to open. We want to fix that efficiency. So we've derived 3 new solutions that will help increase efficiency through 2 different methods. One cuts down human interaction. It makes it a little bit safer, and we can take away some of those safety steps. The other reduces the amount of steps entirely.
So some of the solutions, we came up with 3 total solutions. Our first solution is laser grid inspection, which reduces the number of steps in the original manufacturing process by eliminating the need for a CMM research for data collection. The second solution we came up with is a smart can tracking system, which essentially partly automates the entire manufacturing process, and it even reduces the amount of packaging time by about an estimated 67%. Our third solution is a combination between a CNC machine and a robotic arm. This would almost completely automate the manufacturing process by eliminating the need for human inspection throughout each stage of the original manufacturing process. Additionally, it would also significantly reduce the amount of time it would take to complete the process, as it is a very long and tedious process.
After we had our 3 solutions, we had to put them through 5 design requirements. Firstly, we wanted to cut down on cycle time. So our goal time, or our goal percentage to cut down, was 25%, so that more parts could come out per day. Additionally, we wanted to limit the amount of movement the high explosive materials would be going throughout the process in order to guarantee no mishaps happen or no exposure happens. Additionally, we wanted to increase space efficiency and reduce the footprint by 33%. And most importantly, we wanted to maintain Pantex's rigorous safety and quality metrics. After going through
those requirements, we determined that our product, Barracuda, would be the combo CNC machine and a robotic arm.
This system allows you to take 3 separate machines that were originally in 3 separate bays, combine them into one bay. Our first machine is the combo CNC that combines both the mill at the top and the lathe at the side. The lathe functions along a track, which allows you to run the lathe and cut at any angle you might need. Our second machine is the robotic arm, which at the end of it has a water-heated suction cup that can attach the material, come back, retract, spin, and then deposit it at the CMM simultaneously. This is able to give you all your measurements, make sure you're still within all of your tolerance levels. Now, I know you're wondering, what if the arm drops the product? Well, there's a net that is attachable to make sure that none of the product is damaged while it's being dropped. And as well, the safety system is integrated with it, are fully integratable with your current safety systems. So everything that y'all use, like say a water system gets cut off, the whole process is shut down. Someone can enter in, fix whatever problem it is, and leave. This also greatly limits the human interaction with the HE materials.
The Barracuda redesign is ambitious. However, it is also viable. Combined mill and lathe CNC machining systems already exist. The main difference with ours is that it would be fully enclosed and equipped with a safety net to comply with DOE safety regulations. The water-aided vacuum pump that our robotic arm utilizes is already used in CNC machining to hold high explosive materials in place, making it a proven safe method for transporting these materials. Additionally, robotic arms are frequently used in manufacturing to reduce human intervention, making it a tried and true method to increase efficiency. This solution has an incredible impact on your current system. It removes 2 human packaging and transport steps, decreasing transportation distances by 50% and saving 1 hour per part. It also utilizes space more efficiently, allowing for increased production and increased efficiency. What do you say to swimming with the Barracuda? Thank you, and any questions?
One question, since you mentioned the potential of dropping materials, I'm curious what you think is maybe an acceptable rate for how many materials are dropped per number of operations.
0.
Acceptable rate aligns with Pantex's acceptance rate.
So what do you think is a realistic range? Because we know nothing's 0, right?
Yeah.
We talked with some employees and we found that the accident rate for the current system is around 0.74% per 100,000 work hours. So our system will either maintain or reduce that current rate.
Partially answered my question that I had written down here about 2 operators that you would reduce. So in your design and your system, how many operators are needed, or is it all robotic?
The only human interaction that would be per bay would be the person bringing the material into the bay and leaving. And then there would be an operator operating the CNC machines and the CMM.
This would be done externally from the bay as well in a secure location.
You claimed in there that you would be able to save 1 hour per part. How did you calculate that?
Do you want me to go into that? Okay. So in the previous process, through some interviews, we found that when moving between a mill and a lathe machine, high explosive materials need to be packaged into AN cans, and that this process took at minimum 15 minutes to package. Additionally, we found out that each door takes about 8 minutes to go through with the double blast doors moving from bay to bay. So we had 15 minutes to package, an additional few minutes for paperwork, which we weren't really sure about a number, so we said it was 0 to keep it on the conservative side. So then we had 8 minutes to go through the door,
another 10 to 15 minutes to unpackage, place it to the next machine, and then this entire process is repeated again to move from the second mill or lathe to the CMM machine, which adds up to about an hour.
Yeah, I have just one quick question. You presented 3 solutions as potential solutions, and you chose the one that you chose in terms of the CNC mill and lathe, and robotic arm. And, what was? How did you arrive? How did you distinguish or discriminate between the other solutions?
So one of our solutions was the laser measuring system.
Yeah.
And with the current technology we have now, the laser measuring system isn't quite as accurate as the CMM. And we know with nuclear reactive materials, you really need a high level of accuracy. And so it's just not very feasible in the workplace.
And our other solution with the smart CMM or smart cans, they would implement a weighing system and would automatically transport the materials. But with the sheer amount of cans at the Pantex facility, we asked and we learned that they had just got 300 more. Being able to change all of those cans, keep the systems up and running for each individual can would just be unrealistic and a huge sink and not worth it for the amount of effectiveness it's bringing.
In comparison, this solution for you, it accomplished a lot more than the cans or the laser grade inspection method.
Are all 3 parts new to the system, or are you reusing the lathe? You're reusing the CMM?
The combo CNC, the mill, and the lathe, that's new, and so is the robotic arm.
CMM.
The CMM is y'all's original CMM.
Okay, thank you, Team Barracuda. All right, so Team Counterattack, come on up. Whenever you're ready.
Howdy! I have a question for you. You see these 2 images over here? One of them is a fake logo, and the other is the real logo. Can you tell which one is which? Do you think the top one is the real logo? Raise your hand. Okay. So do you think the bottom one is the real logo? Raise your hand. That's quite a lot of answers. Well, if you chose the bottom one, you were right. It is. However, the issue is that every single day, people working at the Pantex nuclear facility need to look through thousands of logos to determine which one's real and which one isn't. This is an issue that they face, and they have to go through every single label. We, Countertech, are here to solve that problem.
Seizures of counterfeit products at U.S. borders have increased tenfold over the past 2 decades. The total value of seized goods, if they've been real, reached nearly $1.4 billion in 2018.
Counterfeit electronics are flooding the market, and as CBS 2 investigates, they're cheap, dangerous, and the proceeds could fund terrorism.
We're Counterfeit, here to present on how you can more rapidly identify counterfeit hardware and electronics. Now, part of why counterfeits are such a big issue is the fact that it's so widespread. It affects everyone on all levels, from your average consumer to giant companies to even governments. In fact, a little while ago, a armed service committee had found that over 1 million parts in the Pentagon supply chain were counterfeit. And these parts were in everything from their missiles to their computers to helicopters. And while there are current methods to determine if something is counterfeit, they're not the best because the majority of them rely on human expertise to hand check, which is a problem because for starters, you need people to be highly trained and experienced to detect if something is counterfeit. And because they're humans make mistakes, so you can't reliably have them detect every minute difference that could signify if something is counterfeit all day, every day. And also, it could take a really long time to determine if something is counterfeit, from a couple of weeks to months on end. Now, in order for our design to be more optimal than what's currently in place, we have determined 5 design requirements. For starters, speed. Our system needs to be able to, the moment we give it something, determine if it's counterfeit or not within about 10 seconds or less. It also can't take up too much space. It can't take up a whole building. It's not optimal. So it needs to take about 2 by 2 by 5 meters of footprint total. It also needs to be able to retain data well in case we need to recall it or get in touch with the manufacturers. It needs to be able to hold about 30 days locally at a minimum and be able to export 10,000 records at a time. It also, because these are nuclear weapons that y'all are dealing with, it needs to have at bare minimum 99% accuracy at the worst. And it also needs to be able to analyze and handle at least 6 objects every minute.
So now, for our first solution, we thought of an acoustic resonance system. So the way the system operates is that pretty much you're going to be generating a resonance, and that resonance is going to be applied to the hardware piece. We thought about it, and it may work. However, there's some issues. So pretty much, it's a very delicate system. So any interference, any external frequencies, can really affect the measurement. The second solution we thought, it was on a binaural record system inspiration. So pretty much similar to a binaural record where you pass a needle through to sort of on a surface. You can inspect the surface with that and check for any pretty much irregularities. However, it's not very practical since it can take a lot of time to analyze a whole piece, which led us to our final solution, which was an automatic computer vision system. So the way it operates is that you have a conveyor belt that carries pretty much the weight or the hardware piece. Then you have a camera system that's sort of measuring in real time the live feedback. And then sort of it's using a machine learning algorithm to pretty much detect whether it's a real part or a counterfeit based on the data that the model is trained on.
So what you're saying about like the specific physical toolings to machine, to train it on a model for specific tools and attributes that we have it trained on. So some examples are labels and other aspects that we have it. Some things are like size, shape, color, material, and texture. And these are all things that can't be done with a camera all by itself. And these are things that, you know, have been really common for detection and tools that we've used previously.
So, like we said, how does our solution relate to Pantex? Because we were talking about how counterfeiting is a problem in all industries, where big businesses are direct to consumer. So, but for Pantex specifically, since y'all are working on nuclear weapons, you're dealing with a lot of hardware, fasteners, nuts, bolts, and electronics. Right now, for fasteners, y'all have people that look through and look at the logos on each fastener and make sure that it's the correct one, but that can be repetitive and lead to human error in the long run. So it's not very cost effective either, because it requires training and humans. And it can even lead to safety concerns, where like, what if one of the components is counterfeit and it causes damage to the person looking at it? So our advantages of our computer vision system are that it's a machine learning model, so everybody's eyes are different. If you use a camera, though, it's more objective, and it's trained on thousands and thousands of images that we just don't have the memory for. So it'll look at higher resolution and make sure that it's not counterfeit. Additionally, it's automated, so you can just set up a bunch of widgets to go through the machine, and it'll get it done over time. And lastly, it precisely sorts it into a counterfeit or suspect box and an accurate good tool box. And we did some research on existing anti-counterfeit machine learning models out there, and they can get up to 99.7% accuracy. And these will only get better with time as we use more and more data. And you can see in the model that we were able to make just like over a few hours yesterday, I was already able to get it to start identifying fasteners and screws. Now I'd like to show you how our prototype works. You would take whatever widget you would have, and it would be get on the treadmill, and it would roll through. And I get under the camera here, then it would take a photo, run it through the machine learning system, and determine if it was counterfeit or not, and switch which way it would go out.
So what everyone has been saying is that, you know, obviously counterfeits have become a big issue. This is not, you know, obviously the issue that has been only considered with Pantex. So we got that about that, you know, a lot of times people think that this problem is like very complicated. It has specific tests that test multiple things, but a lot of times these tests are just as simple as the label, the color, or the shape. And so we thought about that, and we thought by automating this process, we were able to get most of all the problems that a lot of people have with counterfeits. And so, you know, obviously these are just big problems. And, you know, if all our counterfeits seep into our defenses, will we be able to protect ourselves from all these things? Thank you. Taking questions after this. Thank you.
Judges, so are you identifying counterfeits, or are you identifying changes, anomalies to the baseline?
So actually, we can identify both. The system is pretty much like trained with like data. So for example, one day you can get there and train the model with like existing pieces that you already know it's like a genuine part, and pretty much you can check like if another one is fake, and also check like any irregularities on the piece, since the model can't really detect like those tiny details.
How much would a system like this cost Pantex?
So generally speaking, it really just depends on like what you wanted to train it on. So there's a variety of different models, different tools that people have used in the past. So it really comes down to what you want and specifically what you need for which specific model. So obviously, like if you're using a widget for like a battery, for example, it's probably going to cost a lot cheaper than that. So I would say probably around the ballparks of like something that would be a lot more manageable for. It'd be something more in the ballparks of like maybe like $1 million to $2 million just to get that system running.
And as if you're using it for more like electronics and microchips, you'd need a more precision camera, and it costs more. But depending on how big or small parts you want to use it on.
At the the end of the day, though, it will be cheaper than using human force because this is far more accurate than humans. So it removes the error of humans and basically reduces the amount of money you will have to spend if something goes wrong.
Especially since when you also have to ship a lot of your testing stuff all the way to other facilities just to get all tested out. So this is just getting rid of all the initial bad things that are wrong with it, so that we can use the actual products that need to be tested more properly.
Once you pay for the model, you're going to be using it, and over time the model's just going to get better and better. So it's going to be an investment.
You said this is looking at the physical characteristics, and I'm understanding we're using a camera. Other physical characteristics that might contribute to decide if something is suspect or counterfeit is maybe weight. Have you discussed that at all?
Yes, we did. We were thinking of a system, so over here, when it does this initial testing, after that it goes to this plate right here. Over here, we're going to do impact pressure testing, which basically weighs this basically our rigid, and based on its weight, it will determine if it goes into the good pile or the bad pile.
In your video, there was several references to batteries.
Yes.
And I understand the risk of fire from batteries, but how are we going to test batteries to make sure that they're capable?
When we were interviewing Pantex employees, one of the biggest problems they said is that on C&E batteries, they're fake counterfeit batteries where the C&E logo is just closer together. So using a camera system, and you can look at the batteries and detect if it's counterfeit.
So I'm just curious. I mean, you're looking at an image through the camera. How is the item getting? Is somebody putting the item on the conveyor belt?
Our idea would be to have like a big funnel that would change the size depending on the item and allow one item to go through at a time. But we didn't have time.
I'm just curious about how you ensure. First of all, as it goes to the conveyor belt, depending on how it's put on the conveyor belt, you're going to change the aspect of the item, right?
The camera's always at a fixed distance, and the model would be trained on many different angles for each item. So it would be able to handle
even the part that's in contact with the conveyor belt.
Ideally, there would be like a clamp to like grasp the item, like sort of like rotated, so like the camera can get all angles from the item.
So would that almost be like an X-ray machine? Would you have someone, moving it around, or would that be automatic?
Automatic. It would be completely automatic. It's just you need somebody to put the items there.
Last question. I'm curious on your machine learning algorithm if there's small anomalies that are within the margin of error. Is that going to cause a hysteresis within your machine learning model to allow a larger tolerance band over time, or how do you prevent that from happening?
Well, our machine learning model can learn as well on your data sets. So if we find that, this is a bad set, we can train it further to basically help it recognize which one is good.
So you're training on a baseline, you're not training on every piece going through.
We could. It's like we can, but we also shouldn't because too much data can also cause issues. There should be like a set amount of test data and a set amount of training data.
Okay, thank you, team. Precisioneers, come on up. Everything.
Yeah, sorry. Yes, we did good. We used it all the time. We did.
We're going to do if your video doesn't start when you click once, you're ready.
Howdy, my name is Aljon. I'm Connor. I'm Chris.
I'm Clayton.
And I'm Sarah, and we are the Precision Years.
More and more emergency officials are headed to the scene.
The blowdown stack still emitting flames.
2 people killed, several injured. All too often, OSHA finds employers are complacent with machine safety features.
Found an ignition source resulting in a flash fire.
Where 2 trailers were destroyed, fatally injuring 15 contract workers.
Would you want situations like these at one of the nation's most crucial nuclear facilities? At Pantex, the pillar of nuclear deterrence, every situation matters. The work is done under extreme conditions. Nuclear, high explosive, and manufacturing risks require a serious and thorough focus on safety. Specifically, manufacturing techniques must be accurate and precise in order to ensure that risk is minimized. Human error plays a major role in 60 to 90% of manufacturing accidents. A large portion of human error is attributed to complacency during repetitive tasks. That's where we come in. Here at Precision Years, we have worked to develop a solution that helps minimize the risk presented by human error. We redefine what safe looks like in the nuclear enterprise. Our goal is clear. Limit the amount of repetitive tasks carried out in the manufacturing process using automated, efficient technology. Together.
Sorry, I can't read that. But imagine this. You are a technician at Pantex. A shipment of 10,000 bolts just came in, and it's your job to ensure that every single one of them is up to the safety standards. So you begin your task. Start scanning the bolts. If you bolts in, you feel fine. As you reach 100 volts, 200 volts, you begin to grow tired, a little bit bored. Now imagine doing this for hours on end. Mistakes are bound to happen. Mismeasurements happen, a broken piece slips through. A research was done of over 200 industrial accidents, and it was found that over 50% of them was not caused by machines, but rather human error, a collection of small human errors found through repetitive actions. Currently at Pantex, 80% of the manufacturing process is done by human hands. This leaves a lot of room for error. Because the mission is to create a reliable nuclear deterrent system, it is important that we reduce this. So our problem is the human error in repetitive tasks. We narrowed down to 3 main issues. As humans, we tend to do things as best as we can, but it is inevitable that we make mistakes. And even a 1% mistake can cause a huge issue down the line. As humans, we are not very consistent in the things we do. Sometimes we feel tired, sometimes we're having an off day, and that will affect our speed and longevity. We can only work for so long in a day, but there are so many hours left that can be used doing other things. So we need to create a machine that solves all these problems.
And from the main problems we identified 5 design criteria. The first one, longevity. Through our research, we found out that an average worker in a manufacturing job will end up working there for about 5 years worth of working hours. We would like to double that. We want to have around 100,000 hours of working operation hours. Second, speed. Through our interviews, we found out in the XRT or XRF process, whenever you scan, if you had, for example, 1,000 components and you had to scan them and record the data, it would take about 3 hours, which is way too long. That's a rate of about 5 components a minute. We're aiming to have 10 components a minute. Third, precision. Due to security reasons, it's difficult you have to use pen and paper to write down data. And whenever humans typically, humans can sometimes have errors. And so, for example, if you're writing down a number like 25.5, there's possible like a 1% chance of them writing down 25.05. Fourth, versatility. Through our interviews, we also found out that about 80% of the products at Pantex is about the dimensions of a desktop, which we found to be about 48 by 24 inches. And we would like to double that, and we'd like to have our dimensions be 72 by 36. And finally, ease of use. It is crucial that every technician at Pantex is able to use our design.
Okay. Based on our 5 design criteria, we've come up with 3 solutions, with the first being a fully autonomous robot arm. This arm is designed to solve one simple problem in manufacturing process. However, it is still limited to only one function, but it's also able to do this 24/7 throughout its entire lifetime. Next, we've come up with a manufacturing machine learning glove or MML glove for short. This glove is initially done by controlling with your two arms, but eventually through machine learning it's able to work fully autonomously, freeing up your hands, allowing you to do another task. Lastly, we thought of laser sorting. This is something that uses optical technology to differentiate material based on its interaction with light, which allows for mass sorting at a quick pace.
With these design solutions, we developed a Pew matrix and compared those solutions to our 5 design criteria. In this case, the analysis gave us that the MML glove was the most valuable solution.
Now, our prototype. So this is called the manufacturing machine learning glove. Say we have about 10,000 volts that we need to scan for the material composition. So instead of that individual person or that person individually checking each bolt, instead all they have to do for this product is put their hands into the sleeve, pick up their XRF tool, and begin the scanning process. Now, in order to collect that data, we have a foot pedal that begins the data collection. And whenever you measure our bolts, then you can the numbers can be checked by the camera up on the top, where it will take those numbers and put it into an Excel. And so after about 50 to 100 repetitions, you can end the data collection with the foot pedal, and you're free to get out the machine. So now that we finished this, the machine learning will take that and start working on its own, taking that data from those repetitions to continue scanning the rest of the bolts.
Now, how can our device help impact your company? So first, a device like this in using robotics and AI can last up to 10 years, given annual maintenance. It's also very efficient. Once the data is trained, the device is trained, it can do these repetitive processes automatically, while allowing skilled technicians to do work on the side. It's also very versatile. Given the design constraints of size, we know that 80% of components coming through Pantex are about the size of a desktop. This device is about 50% bigger than that, so it should be able to fit all of these components. This is how the MML glove changes the game. Thank you.
Judges, any questions for the precisioneers?
Yes, I'm assuming this is a glove box. Did you look into whether Pantex would have to invest in additional glove boxes, or what are your thoughts around that?
Yeah, so I wouldn't say it's a glove box. It's just it's a box that you put your hands into and you work with it. But the AI also has like set parameters of the area in which it would operate in as well.
I didn't capture everything from the decision matrix you had there, but it looks like it's a repetitive task. I'll admit I don't do this much, so I can't tell you how it works. But why is the gloves more efficient than the robotic arm that looks like you do a similar thing?
Yeah, so the robotic arm is just one arm versus our gloves is 2 arms. So it essentially is able to do more with that.
And what's great about this is that it can work with many different custom bolts. So say we only need like those 10,000 volts for one product or one weapon for that time. It would take a long time if we just had a machine that would just work on that. So this is just kind of like a replace to aid in that tooling process.
You also said, and I may have misunderstood this a little bit, the average person works for 5 years, which is about 40,000 hours if I looked at that correctly. And I think you said we'd like to double that. Is that doubling their retention, their productivity, something else?
We want to double how long they work there. So, for example, this is just from the resources and the data we received. A person may work at a company for that amount of time, that many working hours. We want ours to go for around 10 beyond that.
So how does this make them work there
So first off, with humans, you can only work during the day. With this, theoretically, if you wanted to, 24/7, no tire. And on top of that, the data that you would get from it would be more precise, more accurate,
and fast.
Did you guys use one of your voices on the video?
Yes. That's it.
Anything else, judges?
How did you calculate the tool's lifetime? Expected lifetime.
Thank you.
Could you repeat the question?
You had on one of your last slides, you had the 2-year tool lifespan.
Yes, the lifespan. So whenever it's the humans, this is so with humans you operate with it, and that takes some of the load, so it can that's the math we have behind it.
Yeah, it was mostly comparing to robotic systems like arms that exist now and their lifespans. I was kind of researching on what robotic systems that exist now they utilize this type of technology, what their lifespans are, kind of estimating that type.
So in terms of years, this is going to become obsolete?
No. It's 2 times, so 10 years.
So based upon the human anticipated working at that job. And then the other question was about ergonomics. It kind of relates back to the glove box thing. You can put your shortest person in there. What if your tallest person is going to use this?
Oh, that was just because the gloves that we had access to were small and we don't want to break it. But it should, in a practical design, it'll be a lot bigger, to really fit your hands in. There's a lot of different, there's going to be different sensors and things that are also on there, so it'll be a lot more.
There's also a compression aspect that really helps with the tedious movements, so it'll kind of have a suction over your hands.
All right, thanks team for this.
Hi, Zachary. Thank you.
Okay, Team Toads. How to get settled in where you want to be. Who's starting with this? Okay. So the large black button is forward. Just go sit there and your citrus on it. Sometimes it's just flipping to the two lines if it doesn't start messing with it. Some is easy to do. But don't get too it's good for one. It's fine. Just do one.
Howdy. Howdy. I'm Kazar. I'm Bruce.
I'm Fabian Ortiz.
I'm Alyssa.
And I'm Alex. And we are the Toads. I didn't come up with the name. So now I'm going to ask you guys a question that I already know your answer to. Have you ever dropped something?
Yes.
Maybe the result was a coffee spill. Or in the worst case scenario, maybe a screen cracked. No worries, no biggie, no problemo. Simple human mistake, not very big consequences. Now let's say you dropped, I don't know, radioactive material. Biggie, problemo, worries. One simple human error has catastrophic consequences when you're dealing with hazardous materials. There is no room for human error at Pantex. How? How can we mitigate human error at Pantex? Easy, right? Eliminate the humans fully. Automate, robotics, AI. I know that's a word everyone's throwing around these days, but it's not that easy. With automated robotics comes their own set of challenges. Cybersecurity, Tempest, for example. Safety, reliability. The line is thin. The problem is complex. The question becomes, how do we reduce human error and risk with advanced robotics while making sure cybersecurity and safety are never compromised?
I want you to take a look at this hierarchy of controls. Okay, so currently Pantex is operating at the level of engineering controls and below. That doesn't sound very promising when it comes to nuclear and high explosive materials. So our goal is to raise that level up to the elimination and substitution level by completely eliminating the human and any possible human errors by substituting a robotic forklift in the place of the human. So that means with all of our design requirements, we have to limit human error. We have to make sure that it's cyberly secure. We have to include fail-safes and make sure it is absolutely very, very, very reliable and cost-effective. So some of the other solutions we came up with is the overhead gantry, self-driving pallets, and automated truck loader. So only the automated truck loader completes all of the tests. It solves all of the problems. Introducing the toter.
Truck loader.
Pantex plays a vital role in safeguarding our nation, maintaining and handling some of the most sensitive materials in the world. For decades, it has been the cornerstone of security and safety, where precision and responsibility are non-negotiable. But with this mission comes danger. Exposures to hazardous materials can cause lasting harm, damaging lungs, skin, and vital organs. Protecting the people who make this mission possible isn't just important, it's essential. Yet inside the warehouse, traditional equipment like forklifts add even more risk. They operate in tight spaces, surrounded by people, and accidents happen. Collision, tipping, and heavy load slipping put workers in harm's way. Every incident threatens both human safety and critical operation. That is why we created Toter.
So you might be wondering how we came up with the requirements for our arm. So mainly we need our arm to be able to lift up a pallet of about 100 pounds and 4 drums about 60 pounds max each. We added a 30% weight tolerance to this, and we calculated using 500 pounds of load with our arm being about 12-foot extension. We wanted this so that the arm can go inside of pickups, semi-trucks, etc., and it can reliably grab the pallet, go up to, if required, the pickup is higher of elevation, there's no loading dock, etc. We are accounting for this with the arm. We're using an arm that has pistons that attach to here. We're using 4 pistons across, 2 this way and 2 this way, so that extends our arm, and then 2 more pistons actuating our actual forklift lift. And that ensures that we can lift this up and actually have a total lift capacity of 3,500 pounds, which gives us a margin of safety of 7. So you might be wondering how we're actually going to move this vehicle of about 800 pounds total with our load plus all of our systems. We're going to be using 2 lead iron phosphate batteries, and we're going to use these batteries to power our 2,000 watt motors that are going to drive our robot. Most of our power is going to go into this actual motor, and this motor is going to have a gearbox with a gear ratio of 20 to 1. And then this battery is going to ensure that we are using efficient, cost-effective solutions for our system.
As you've heard already, we are creating an autonomous robot. We are not having humans interact with it, just oversight. So we have 3 sensors operating inside of the robot. We have a LiDAR, a ADAS, an automated driver assistant system, and a DS457, which is just a basic barcode scanner. For our systems, our sensors, they have to have calibrations for each month that they are operated. And then they also have to have a self-monitoring system to where the ADARS is going to learn through itself without human interaction as much as it can. We are going to feed it information of a digital twin with our warehouse for our Pantex, and we are going to calibrate it for any requirements it may need. So I'm going to ask you a question. Which of these numbers do you want to pay? I'm assuming the answer is $32,500. And right now, from our research, Pantex is paying $66,000 in forklift operations. We are going to half that, and we can guarantee that.
Yep. So basically, to integrate this new robotic system, considering all the autonomy, you may consider, well, how hard is it going to be to replace all of our very conventional, very well understood systems with an autonomous system? How do we even integrate this if we have the robots in front of us? And it's actually not as hard as you think. It's 5 steps. So who here knows what a Roomba is? Yeah. So the more advanced Roombas have basically map out their surroundings. I think this is a good analogy. So you would have the robots, you would put them in the locations, in the loading bays, the roads, the sites, and storage magazines where they would be interfacing with pallets. They would map out the location, and with this map, a digital twin would be created. Now, what is the digital twin good for? Well, the robot can basically simulate how it would move through the environment without actually doing it. So that in a case with high explosives and radionuclide materials, it's very important to know that to simulate if a motion is possible without actually testing it, because the consequence there won't be a coffee spill, right? So after it has simulated all of the problems and it has found any problems with this is too high, this is too narrow, then these difficulties are identified, and then the site can be adjusted to allow this to perform optimally. Now, we have been talking a lot about the technical specs, the what, but I want to talk about, okay, so what? Who cares? Well, the near term, as we've covered a bit already, moving in the hierarchy of controls to eliminating the human entirely is as good as you can, is as safe as you can make an environment, that deals with high explosives and nuclear material. And as Alyssa covered here, in the longer term, paying half per year, paying $33,000 per year for the same forklift operations, the same throughput, on top of the reduced safety risks, that's why this is worth thinking about. So overall, you're reducing the human error, and the robot is very robust. It has triple redundancies.
All right. Thank you, Team Toes. Judges, questions for Team Toes?
So I'm intrigued by your operating costs from going from 66K to a year to 33K. That's just operating costs, right?
Operating.
That includes maintenance.
That includes. So this is what y'all pay right now. This is your acquisition. This is your base cost, and then this is your maintenance, and this is your insurance. We did all the research and we calculated that, and now we put in our data, and we found that including the sensors, in the long term, you're paying half. You don't have to pay the wages for the workers. Our insurance is lower than for a regular manual forklift because we have such a guaranteed higher rate of safety.
Okay. What's the initial cost on the itself? Is it different? Because you come up with your own design here, right? With multiple pistons and whatnot. I noticed you did drop something though when you were demonstrating it. So.
That's the human error part. Calculating.
Well done. So yeah, just curious. What's the cost per item going to be? Do you have any idea?
It's base cost per item for a robot, if you were renting from us, $500 to about $600.
We're going to lease it from you.
Listen,
Okay.
you have to pay for the license.
Okay.
How did you verify the 3,500 capacity at Pantex?
So basically, I did torque calculations and used the pistons are used to counteract this torque force acting on this central point here, basically. So where you have a force of 500 pounds across the 12 feet, we calculated the torque from that, and then based on the angles that we need this to lift up the 36 inches up and 72 out, we calculated total torque required, and we used the pistons. We had 1.75 inch diameter pistons by 3.5 feet, 4 of those, and then 2 shorter pistons for these, and that's essentially how we interacted the force.
That would satisfy Pantex requirement?
Yes, it will.
System reliability. Robots aren't perfect. Software packages aren't perfect. What's acceptable reliability for the system?
Because of its self-modulating system with the ARS, it updates in real time when it has any problems at all to the computer. So we calculated that it's around 98.7.
I've got 2 questions. The first one, how do you mitigate when you reduce the risk by taking the human out and you're adding this new technology? Are you not introducing other risks into there? You described a Roomba that's going to go in and map everything. So now I'm thinking there's a pretty significant cyber risk with that data mapping more sensitive areas. And there was a question on the battery. There's a risk with the battery going to some areas too.
I'll take the cybersecurity and then I'll take the battery. So, a little explanation about the ADRS is completely online. You don't have any access to it offline. So, any of the schematics that are so-called saved are only available from the tote.
You said online.
On board, my bad.
Yeah, it would not. They would not be online. They would be on board. So it's entirely local to that device, nowhere else. So it's in the robot's brain.
But it's not communicating.
It does not have it. It can't communicate wirelessly.
The only way it can is if you scan the barcode.
And then you presented some reliability data that suggested this. I think in your decision matrix, it said that this was going to be more reliable than an overhead gantry. Walk through how you made that determination.
So overhead gantry, right? It's first of all expensive to install, and second of all, it's extremely complex. So there's a lot of moving parts, and there's a lot of things that can break. Now, let's say something does go wrong 6 months down the line. Your overhead gantry is now not usable for a couple of weeks. What's going to happen? Now you have to revert back to your human employees. You have to revert back to manual forklifts, and you're back to square one. Versus a toter, if one of them breaks, you still have multiple. It's not one system. It's a bunch of them working independently. So it's more reliable. You don't have to revert back to manual forklifts.
I've got a little bit of concern with a collection of a number of systems versus a gantry, which we already have installed. And we can talk about it later. I think one appears to be more complex than the other.
Okay, thank you, Team Toads. Okay, teams. The good news is you're finished. You did a great job. And I can see on some of your faces, you're sitting out there saying, "Oh, why did I do this? Why did?" Because you're human, and you didn't do things perfectly. Again, welcome to the long line. We're all there. You did a great job. You need to cut yourself some slack. The judges, we're gonna recuse the judges to the next room. You are gonna sit here, vote on people's choice awards among yourselves. Give us some feedback. 2 members from every team, please go through this door here, and you're gonna get really quick interviews. And we will round you up and head to the learning stairs in probably about 15 or 20 minutes, okay?
I hope they're not like
I got in here and I got to program on. They were mostly the entire time. I didn't make really much of it. It's like some little slip slow down frame. I panicked. I wish I yelled. I could. Sorry.
We go now or what? Yeah. He's an expert. Oh yeah. Yes.
all the time. So I will be applying. I think you can.
I don't think it's right.
God. Just to have food outside, I like to have Thank you very much. My first hold on. When I was talking, I didn't like it.
I'll show you mine after. Microscope. Oh, let's go take off.
All right, let's get started. Before we get to the awards, I would like to, I'd like first to thank our judges. Let's thank our judges for being here. And then I would like to ask each judge, and because we started on this end last time, we'll start on this end this time. I'd like for the judges to give you some feedback. I want you to understand feedback is not affirmation. It's not criticism. It's feedback. You can reject it, but you shouldn't. You should lean into feedback. Grow as a professional, right? Right.
Sure. And I think maybe feedback is really important this time because some people will be moving on, right? So
that's right.
I had just two pieces real quick. First, everyone did a really good job. It's intimidating to stand up here to present something to a panel of new people in front of a bunch of peers too. So good job first of all. The two things, one just an opportunity. When you're presenting, you're talking about the solution. Think about new capabilities, capacity, how that can increase with your solution. Not that it's just always gonna be more efficient, but can we do more of something with it? The second one is more going towards some of the videos. I'd be careful of not always showing the worst case scenario for something that could happen, because it's kind of like telling us we're not safe. That could happen any day of the week, and that's not true, right? I think about if you do this to a panel of our senior leaders, you're telling them that 3 Mile Isle can happen tomorrow, and there's no way that can. So I just tone those down a little bit.
Yeah, thank you.
Again, great job, guys. I know everybody's a little nervous, but always remember when you're with your team and they may not speak what they're supposed to, try not to make facial expressions to show that they're like, that's a bad answer. So try to keep that in mind. But overall, you guys did a great job. The thing with trying to not be nervous, you guys are probably way too young to understand the Brady Bunch. But when Marshall was getting her license, she would picture someone in their underwear, and that relieved the tension. So try to think of something funny so that you don't get nervous and upset when you're up presenting.
Hopefully nobody's picturing me in my underwear.
I swear, I am not.
All right. I want to say thank you. Thank you for the opportunity to be here. It's incredible to be around so many of you. I was impressed by a lot of what I saw over the weekend. I saw a lot of effort, late nights, early mornings, a lot of effort. And as an employer, I like seeing people that are willing to do a little bit more, go the extra mile, show up on your weekend, your time off, come in here and work, get dressed up. You guys look incredible today. And it makes a difference, right? When you get ready to do something like this, this is also preparing you for job interviews later on. Use this as reference material for when you're looking for a job later on, because this type of stuff matters. I heard a lot of concern yesterday and this morning about stress and not really wanting to get up in front of a group and talk. And you know, when we get in stressful situations, when we're dealing with challenges, is when we learn. And so, if you avoid it, you're never going to get better at it. For those of you that really struggled with it or were really concerned with it, you did fantastic. For those of you that don't think you did really well, maybe you fumbled a line here or there, maybe you got stuck somewhere, that's okay. Because nobody is going to give you a hard time about it. Maybe if you got good friends in here, if they're really good friends, they will. All right, but you'll get better at it. And the only way you get better is doing this more often. All right. At some point, you're going to go to a job interview, and the same stress is going to be there. All right. Being able to talk in front of a group is a very, very important skill. You're going to be engineers. You're going to go out wherever you go work. You're going to have to talk to people and convince them of ideas, challenge other people's ideas. Your communication skills are vital. Will be vital to your success. So don't be afraid to get uncomfortable and grow. And then again, I just want to go back to teamwork. When I hire people, teamwork is one of the most important things that I evaluate for. Can you work as a team? Can you convince me it's not all about you? It's not about what you think and what you've done, but how have you made a team better, made a team more successful? How have you supported your teammates when somebody misses a line, when they get stuck? Do you help them out? Are you supportive, or are you not? Is it all about you, or is it all about the team? Again, thank you very much.
Yeah. I don't know that I have a whole lot to add to what the other judges have said, other than I'm encouraged when I come to these types of events because it tells me that we're in pretty good shape, you know, in terms of solving the tough problems that this world is facing right now. Way better shape than this world was in when I was in your all's shoes and trying to figure out just what I wanted to eat next week or the next day or whatever else. So I applaud you all for the amount of critical thought you put into each of these problem sets. The only thing I would add, and it's probably been addressed a little bit already, is that the way you get comfortable in these situations is to know your material, right? That's always, there's no substitute for that. It's when you don't really know your material or you don't really believe in what you're saying that some of the uncertainty comes out, especially under a stressful situation, because stress exposes everything, right? It exposes weaknesses, and so I don't think anybody in here has anything to not be proud of. They were great presentations. You did know your material. You can practice some more on it if you really believe in it. This is the thing I tell every one of these groups. If you believe in the things you were presenting here, I mean, as a team, as a group, truly believe in it, don't let it end here. If you thought of some things through this process that you think are valuable to Pantex or to some other sector of business, keep pushing it, okay? Great ideas are born in places like this. And I will tell you that we shouldn't necessarily jettison those ideas just because you're not one of the winning teams right here. Okay? So don't worry about what the results are here. If you believed in what you did and you finished out of the top 3, don't worry about it. Keep pushing it. Keep pushing the envelope on it, and make it a reality later on down the road. Okay? Thanks.
A little housekeeping. Part of this. Go for it. And because I don't want to finish on a negative note, I'm going to bark at you now. Make sure when we finish here, before you leave, I will hunt you down. If you don't, make sure you got all your stuff. I've got all the charging cords I need that don't match anything that I own. Make sure you got all your stuff and make certain that there are no bottles, no cans. Let's don't make the custodian's life harder, right? Okay, just let's be respectful. All right, a few thank yous. First of all, David and his team, We got Cooper back here. We got Giannis over here. We got Olivia. We got Archie right here. How about a big thank you for the team? Let me make sure you know, David's your best friend if you're a winner, because he's the guy that makes sure you get your money. So you want to, and they get loaded in your student account. I'm sorry, we don't have bags of 20s. David's the guy that makes it happen, okay? Two, and this thank you is from you, but also from me. The Malloy faculty members are here. Professor Ball, who came in from San Antonio to hang out with you, he's already gone back. We got Professor Westfall back here. We got Professor Fred over here. Let's say thank you to those guys. You know this event doesn't happen if we don't have one thing. What's that? Sponsor. I'm not paying you out of my pocket, right? Pantex. They live in Amarillo. That's not next door. They gave up their time. They don't get paid to do this. They get paid by your applause. Let's thank our team. Before you leave here, Caleb Helfer, he's the guy that put this deal together. It's Brenda Dillard. She's our new relationship contact. So you want to make sure to say thank you. These other guys probably rounding here. They got lots of them. These are two that make the deal happen. Nice. But accurate. What I think is one of the most important groups here is the mentors. Can we agree? Mentors, please stand up, and you three too, because y'all stood up. Mentors, please thank the mentors. And while we give them really special bag of goodies here, they also have a gold trophy, right? They can take these home. All their peers will be jealous. So that's what we do for those guys. It's instead of money. When we finish, David Cook with the camera in his hand. You just saw him. He was looking at you. You were looking at him. He would like to. He's going to take some photos up here of the winners. He would also like to get some other photos afterwards. So please hang around. But importantly for me, because we have a second round, if you are first, second, or third place, immediately when we're finished, you're coming right over here in the corner. We're going to have a real quick powwow. Won't take 2 minutes. You're going to all come over here. Okay? Everybody agree? Sir. All right, let's get to it. People's Choice Awards. The most, and if you have a People's Choice Award, stand where you are. Be $25 per student. We'll add into your student account. This is, I mean, there's nothing more affirming than winning an award from your peers, right? That's a big deal. The most feasible solution, the one that made the most sense. Barracuda, however you're saying your name. Stand up. Best prototype. Counterattack. Best video. And I don't know among you guys how it was, but on us, we were talking about it. You guys killed it. There were 7 great videos. Great job. But among your peers, Auto Tool. Best overall presentation, as voted by your peers, Toads. And then one of my favorite awards, I like all of them, but one of my favorite awards, and you heard the value of teamwork. One of the big takeaways from this is we force you to work in teams. People you didn't know, we asked the mentors who had the chance to work with you all weekend long. They got together and voted, and they decided that the best teamwork was exhibited by Team Snap Shield. Now, if I announce your name, you're coming up here, and we're going to take pictures of the check. In third place, and winning $1,500 as a team, not as a student, we have Team Aura. Congratulations. Good job. Congratulations. Congratulations. We did it. That's right. You did it. All right. So we're going to hold this up. I can have you all against the back. Yeah, against the background. Back up. I'll stand up with you guys. Make sure you got it nice and level. All right. Smile. All right. Thanks, guys. Thank you. Why don't y'all just go right over there? We're going to meet over there in just a second. I want you to go there. Okay. I think I know the answer, but you should never mess this up. In second place and winning $2,500 with the team, Barracuda. Great job. All right. Here. Gotta get that kind of centered. Dave, do we need to go this way a little bit?
Yeah, just a little bit.
So. Check's not straight.
Check's not still. Let's look
a
little bit this way. But that way we can squeeze you.
There
we go. All right. 3, 2, 1. Smile. Perfect.
All right. I got this. You guys are going over here. Okay. And this year's winner of Aggies Invent Pantex and winning $5,000. Make sure I got it right. Just kidding. Auto Tool. Oh my God. Good job. Good job. Good job. Congratulations. Good job. Good job. I wonder how she feels about it. No, you need to go ahead and be in touch with me. All right. Good.
Here, we got room on
We got room on this end,
I
Jack.
want you all on the All right, 3, 2, 1, smile. Perfect.
Okay, you got it. We're finished. Thanks again for being here. It means a lot to me that you guys would give us up your weekend. Go home, get your homework done, public service down, as mom and dad said. Go get your homework done. Thank all the Pantex team for being here. Okay? Good job, everybody.